There's that at least. So yeah, the last thing that we did was talk about this fancy concept called makefiles, which is going to automate how we can compile stuff. We make one file that's called makefile, and with a capital M, and we give a bunch of recipes for all the things that we might eventually want to make. And once we do that, we get the ability to just type make in the terminal, and it just makes everything that we need for us. It only recompiles the things that need to be recompiled. We talked about separate compilation, how that's important. It doesn't try to recompile everything. If we only changed foo.cpp, only foo.o should be recompiled, and then we can link it together into the program. We didn't touch main, so there's no need. No need to get main.o again. The makefile will do that for us. It will check file modification times and make everything super nice and automated. So we can just type one thing and immediately our program gets built for us in the fastest possible way, which is lovely. So yeah, let's make a makefile for that searching library that we had last time. So let's copy all the code in from last time into today's folder, which is apparently going to be lecture 25. Let's just confirm that I didn't skip anything yet. All right, so let's copy lecture 24's everything.cpp into lecture 25. And also all the .h files, which is just the one. I don't want to type it though. The star expands to anything. So now I have all those files, these three, and I would like to make a makefile to compile them separately and then link them together. All right, so remember our searching library. We have main.cpp, which calls our searching functions, uses our library. Searching.h defines the library. We got the two function names. They're very long, but we remember them, I hope. And searching.cpp had the implementation of all those things. And so normally, in order to compile, we would have done G++, all the CPP files, -o main or whatever. And this is inefficient, right? Because it's compiling everything all at once. Only if I just change searching.cpp, there's no need to recompile main.cpp, but this is going to do it for me. Not okay. So we're going to make a makefile, right? It's going to do the separate compilation for us, and our life is going to be so much better, right? So we need to make those two .o files for our implementation files. We need to make searching.o and main.o. Okay. So we have those two CPP files. We need to make the object files. Those are the ones. All right. So let's start off our makefile with that idea. So I'm going to make a file in my current directory, and it's going to be called makefile with a capital M. That's necessary, right? And so now I'm in the makefile, and I want to write the makefile language. So comments in a makefile start with a number sign, like Python if you've used Python before. So this is a comment in the makefile. This is a makefile comment. And then remember that every rule looks like you got your target's name, what you're trying to get at. You have then space-separated requirements. Ingredient is also another good name for that. Ingredient 1, ingredient 2, space-separated, as many as you need. And then you tab over. Hopefully your editor does that for you, but if not, tab over. You type a bunch of terminal commands that are going to get at that target that you're trying to create. All right, terminal commands and they can be as many as you need to make the target from the ingredients. Okay, so that's the idea. And so let's make a rule to create these two object files. So 2 rules total. 2 rules, 1 for each object file. So I have searching.o. That's my target. That's the thing I would like to make. What do I need in order to make it? What needs to exist? Well, I better have searching.cpp. All right, hit enter, tab over, and then I type all the terminal commands that I need to have to make searching.o from searching.cpp. So that's G++ searching.cpp with a -c in the middle. That's going to do compilation only, -c for compile only. Please make the object file for searching.cpp. Okay, So that's the rule. That's going to make searching.o, and I can do the same thing for main.o. I can spell searching right. Boop. So same concept. To make main.o, I need main.cpp, and here's how I use main.cpp to create main.o. It's that one terminal command. Okay? Any questions about that? And then finally, I want to make one last rule to make the main executable file. I guess that's what I called it. I called it main last time. So that can be the name of our target. All right? All it needs to do is link together main.o and searching.o. So here's the thing that I really want is main, right? It requires searching.o to exist and main.o to exist. And the rule to get there is G++. I assume that I have these, right? These are my ingredients. So I gotta give them together. Searching.o, main.o, link them together, call it main. Usually the name of your target is the name of the file that you're trying to create. So that's the rule to create main from those two .o files. Are there any questions about any of that? So that's the proper make file. Are you ready to see it work? Drum roll, please. All right, so if I say make, and I say the name of the target that I want, so main, for example, that's how you do it. To run a make file, you say make. That's the name of the program that looks for the make file and does stuff, reads the make file language. You say make, and then the name of the target. And notice, I do not have searching.o and main.o right now. I do not have them in my current directory. They don't exist. So this main rule is going to see that and look for a rule to make those. It's like, oh, okay, I don't have searching.o right now. I'm going to run this rule. And so you see it running it right there. Boop. It doesn't have main.o either. So it looks for a rule to make it. And you see it running that rule right there. And now it's got the .o files that it needed by running the rules that created them. So now it can do what it was intending to do all along, which was make the main file. Do we see how wonderful that is? I just typed make main, and it did all of this for me. It made the .o files, it made the main function, made the main file, and it does everything that we did last time. It noticed that the .o files didn't exist, so it made them. It went to their rule and made them. If that is not cool enough, if I make a change to one of these, like, I don't know, if I search for, in binary search land, let's search for 42 or something, let's add something to the end of this. If I change main.cpp, I should only need to recompile main.cpp into main.o. I have not touched searching.cpp, right? So I shouldn't have to remake searching.o. The make file knows that. It understands. If I say make main again, it only recompiles main.cpp. No, nothing to do with searching.cpp. It knows that that's already up to date, and so then it links it. Isn't that lovely? Any questions about any of that? It can figure out what you need and how to get it. That's what make files are all about. An extra nice thing is if you just say make, it'll run the very first rule in your make file. So you put the most important one up at the top, and then you can just say make. And it'll automatically say make main for you. So make, it's like, oh, right, main is up to date, cool. That is the power of make files. So yeah, write it once, and then you can just say make all day long. That's quite nice. Any questions about that before I switch gears into something else? All right, on we go. Next topic. I'd like to talk to you about complexity again. Again, this is not something I really want to test you on in this class. This is a CSCI 41 topic, and so if I ask you any questions about this at all, I promise that they'll be super simple. You can just go to the slides and look up the answer. All right? But I want to talk about complexity to get us ready for CSCI 41, because we're almost at the end of the semester. We might have to take 41 next. So I want to talk about those basic operations and counting them. What in the world does that all mean? All right? So I'd like to figure out how complex linear search is, how complex binary search is. Okay? That's the idea. So I'd like to count all the basic operations in that operation, in that function, right? So a basic operation, it's an assignment, arithmetic, I can't pronounce today, arithmetic statement, it's something involving an if, so checking a simple condition. Those are all doable in like one clock cycle of your CPU, and so I lovingly refer to them as basic operations. Usually it's just a line of code. You can consider that to be a basic operation as long as it doesn't like call a function or like do a loop somehow. So for example, this line, int x equals 5 plus 2. There's two basic operations here, right? So you got the plus, and then you have assignment as well into x. So that's two basic operations total. Are there any questions about that? Is that coming back? So I'd like to do this now for our entire algorithm that is linear search and binary search. I'd like to count all the basic operations in those algorithms. Right? It's going to tell us in a mathematical way how fast linear search is, how fast binary search is. And we're going to see a number, or we're going to see a variable appear because the algorithm is going to depend on the size of the vector we're searching through. So we're going to call that size n. That's what is normally found in the literature, capital N. And so we're going to be using that today. Because I think you can imagine that if you call linear search on a vector v, searching for the value 42 or something, it's going to take a lot longer. It's going to, like, the time is going to be a lot different depending on the size of that vector that you're searching through. Like, if you have a size 3 vector, you can look through it pretty quickly. If you have a size 3000 vector, it'll take you a little bit longer, right? So you got to visit every element at most. 42 might not even be there. You got to try them all with linear search. Okay? So let's count the number of basic operations in linear search first. All right? So here's me copying a screenshot of linear search from a previous semester. It's going to look very similar to the one that we did, right? No real difference, I would say. But look at what's happening. All right, we have to count all our basic operations. So this for loop, for example, it runs this initialization just once, and that's an assignment statement. So that's one basic operation right there. All right. Calling v.size, that's a method call. That's a function call, and let's assume that does constant work inside of it. That's one basic operation to call that. And then we get an answer. We have to compare it with I. That's another basic operation. And this is in a loop. Right? We're doing this a bunch of times. We're doing I++ a bunch of times. So first of all, how many times are we doing this total? That's involving v.size, right? So v.size, let's call that n. Whatever that is, it's n. And so we have our loop initialization. That was one basic operation. And then we do like a bunch of stuff n times because we're looping n times, right? So then I have to like multiply by n. So do n times all this stuff. So some condition checking, some method calls, some I++s, v at I. Let's assume that takes one basic operation to get the value there. Compare it to val to search for. That's one comparison. That's a basic operation. Return I. Basic operation. We'll only ever do that once, though. Let's just count it for fun. We'll have an upper bound. And so all those things have to be like, all these things are multiplied by n because we do them n times, essentially, right? Actually, some of these we do more than just n. But at the very end, if we didn't get there, we have one last basic operation, which is return -1. So all those arrows was like a single basic operation. Does that make enough sense? And some of these arrows are in a loop. So n times, we're going to check our thing, do the body, do I++, right? So that is, let's see here, 1, 2, 3, 4, 5, 6 operations. 1, 2. Oh, sorry. Yeah, checking my notes, I did it wrong. I++ is secretly I equals I+1. So we got to do the plus and then the assignment. So 2 there. So do n times, that's 7 basic operations total inside the loop. 7 ops. And then to end the loop, we do I++, and we compare one last time, and the comparison fails. Right? And that's what gets us out of the loop. So there's actually 2 extra operations if we ever end the loop. That's the comparison, 2 ops at the very end to stop the loop. And then if we return, it's going to be 1 op. All right. This is definitely an upper bound on the number of operations, because if we ever return, right, we're done with the entire function. So counting the body a bunch of times, including the return statement, is kind of silly, but that's okay. That's fine. And so if you add this all together, we get back 4 plus 7n. That's the number of basic operations total to perform linear search on a vector, which is like the worst possible case. Are there any questions about that? Does that make enough sense? Because it is now quite clear, right, that if your size is bigger, like if n is huge, if it's n is 1,000,000, you have a lot of basic operations to do. You have to spend a lot of time looking through that vector. That's your bottleneck. Otherwise, if your vector is super tiny and it's only got 5 elements or so, you don't have to spend much time, right? That n, if n is small, the whole thing's small. If n is big, the whole thing's big. Like the amount of work you do increases in like a straight line, and that's maybe one reason why it's linear search. That's why they call it that. All right, so are we happy with this? Because the analysis of binary search is much more difficult. I want to make sure we're on the same page for this one. All right, on we go. Binary search time. So here's me copying a previous version of binary search. It looks the same to what we did in class. But let's take a look at that. All right, so basic operations at the start. These are outside of loops. So set low to 0. Sure, that's one basic operation. Set high, assignment. B.size minus 1. I don't know. 1, 2. Sure, something like that. So outside of the loop before it happens, we have 4 basic operations. And then we have a loop, right? We have a loop, so we have to compare low to high. That's a single basic operation. Do some mid calculations, so plus equals, compare equals, plus compare equals, minus return. All right, and then a return at the very end. But all this stuff is in a loop. And then the real question is, how many times does this loop iterate? And that is a non-trivial question to ask. All right. So let me show you the analysis there. I'll tell you more about this in CSCI 41, I guess. But what happens when we binary search? We have some giant vector we're looking through, and we look right in the middle of that, right? We look right in the middle of that, see how that compares to what we're looking for, and then we chop off half of the vector based on what we've learned, right? So after one iteration of the loop, essentially we're looking through this vector. It's a little bit smaller. It's half the size. Does that make sense? And then we look in the middle of that. So in the worst case, like we look and it's not there, we have to chop off half of it. We look, it's still not there, we have to chop off half of it. Look through this side of it. Look through this side of it. And it gets smaller and smaller and smaller by half each time until either we find the thing at the very end, or we've run out of places to look, like our search space is empty, right? So in the worst case, if that's what we're trying to calculate, how many times can we possibly have the size of our search space and still be in this loop, have this loop not be finished, right? Have there actually be a search space to look through still. So if you think about that long enough, how many times can you divide by 2 and still have something in it? It is on the order of log base 2 of the size of the vector times. That's how many times you can have it. It's like, it's exponentially getting smaller, and so logarithms come into play. That's the idea. So for example, if we had a Oops. Python 3, import math. If we had a size 100 vector, you'd need about 7 tries until you're out of search space. You'll have to chop off half of it. You can do that at most 7 times. That's the idea. Are there any questions about that? Like that is the number. That's how many times this loop will iterate. That's how many times you have a search space that is still valid, that still has something in it, at least one element of your vector. Because then once low and high pass each other, we've ran out of things to look through. That will take, at most, log base 2 of n times. Log base 2 of n halvings, rounded up. I'm good with that, because it's a non-trivial analysis. It's a little weird, but hopefully my explanation makes enough sense. That's how many times the loop is going to iterate. So instead of like do n times, it's do log base 2 of n times. How many things are we doing? Let me try and count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Alright, so 10 things inside the loop body at most. We're just looking for an upper bound here. 10 operations. And then finally, if we get out here, we didn't find it, we return -1. So that is 1 more at the very end. So that becomes, what? 5 plus 10 times log base 2 of n operations. Are there any questions about that? So that's the analysis for binary search. And now I get to prove to you how much better binary search is. So regardless of whatever our analysis was, like it was something times log base 2 of n plus something for binary search, it was like something times n plus something else, some constant for linear search. Regardless of whatever those constants are, doesn't really matter. Like it was 10 for us here. This one was what? 7. Does not really matter in the end, because watch what's going to happen. So linear search, it's going to look like a line, right? Y equals mx plus b, we've renamed some variables. So that's linear search. That's how much time it's going to take for n. This is as n's increasing, n's on the axis. Linear search. So as the vector gets huge, this is how much work you do. The vector's this size, this is how much work you do. Yeah. Binary search, even though like 10 is bigger than 7, asymptotically, binary search will win out. So even though it like starts out taking more work, as n gets large, this is the graph of a logarithm, right? Binary search takes a lot less time. Binary search. In the end, it's always better. And we really only care about it for large n anyway. Better in the end. Any questions about that? Does that make sense? If I made a horrible binary search implementation, like C ended up being like 1,000,000, and I made a super fast linear search, like I was able to get E to be 1 or something, even with that, eventually binary search would win out. Just logarithms are smaller than n's. Log base 2 of n is much smaller than n always, for large enough n's. No matter the constants you put out in front. So we're talking about large n that way. Okay. So binary search is going to be so much better. If you have a size 1,000,000 vector, you essentially have to do 1,000,000 operations with linear search. And if you had the same with binary search, it would take you 20 operations. 20 versus 1,000,000. Logarithms are smaller than the numbers themselves that you're taking logarithms of. All right? Any questions about that? That's a new idea. So this is ends on this axis, and this was operations on this axis. Let's put that in blue so that it all looks the same. So yeah, that's our analysis. Linear search is not as good as binary search. So if you have sorted information, it is much better for you to use binary search instead of linear search. You will save a lot of time that way. All right. So one of the very big things that we learn in CSCI 41 is how to put into words this idea. Like one algorithm is better than another. And we do this kind of analysis. Eventually, in the end, we notice that these constants and things don't really matter. Really, what was the difference between binary search and linear search was this log base 2 of n versus this n. All right? And so there's a notation that involves chopping off things you don't care about called big O notation. And here are the rules of big O notation. You take your highest order term, so like we had, let's do it for linear search. We came up with 7n plus 4. For linear search, you take only the highest order term, and so the plus 4 goes away as n gets large, so we chop that off. So we have 7n. And then you also drop any constants out in front, and that's your notation. So now we've just turned this into n, we say, all right? And then you slap a capital O at the front of it and put the answer within parentheses, and that is what you write it down as. You say that linear search is big O of n. That's the idea. So we took our analysis and we kind of simplified it. And that is just a shorthand. It's for us computer scientists, mostly mathematicians like it too. And that just tells us how fast, generally, how fast this algorithm is. How big something's going to grow over time, right? So we use this for algorithms a lot. Because we're going to end up coming up with mathematical formulations of how fast they run, how many operations they take. Okay, that's the idea. So linear search, it was 7n plus 4. I don't know what I was doing in a previous semester, but I wasn't doing the right thing. Miscounted. But still, in the end, it doesn't matter, right? Linear search, we say, is big O of n. So we write it like this. And another word to describe O of n is linear time. So algorithms that are classified as O of n are called linear time algorithms. They take as much time as the size of the thing you're going through. Right? There's a whole class of linear algorithms. And then binary search looked like this. Probably got the numbers wrong again, but who cares? Because you chop off, you remove the lower order terms, like the plus 4, so you're left with this. Then you chop off the constants out in front, and so you're left with this. Log base 2 of n. So we say, you wrap an O around it, binary search is log base 2 of n, is what we say. And so another word for that is logarithmic time. And logarithmic time always beats out linear time. Okay? That is the idea. Any questions about any of that? Let's see, do I have... So that is the way that we like to analyze our algorithms, because my laptop is much slower than the giant computers in front of you, and so any algorithm is going to take longer on my computer than yours, but it might be the same algorithm, right? We want a number that tells how it's going to run on any computer. That's what big O notation is all about. But if you really wanted to time something, here's how you'd do it. You'd use the CTime library. And I can't remember. I might be forcing you to do this in a future lab. Can't remember if it was this class or CSCI 41. There is CTime as part of the C library. We use this to seed our random number generators, right? But there's also a function in the CTime library called clock. And that's it looks at the clock inside of the computer and reads the time off. If you call this function, it gives you back a clock t. That's the type. It's just a big number that represents the number of seconds since January 1st, 1970. And so you call that, actually it's a bit more accurate, in fact. You call that, you get a clock t back, and then you run your algorithm, and then you tell C++ to look at the clock again. What time is it now? And then you just subtract the times, right? So you got your start and your end, you call clock twice, and then you subtract n minus start, and you divide by a constant that's built into the language called clocks per second. It's in the library. and that will convert however it's using to record how much time it's taking. It's not a normal amount of time, not a normal number, and so this converts it back to seconds so that you can use it. And these are all integral numbers. Like clock t is a large integer. Clocks per second is a large integer. So if you actually want seconds with decimals involved, you got to cast one of the sides of that division to a double. So you can do the first side. Set it cast double, n minus star, divide that by clocks per second. That will give you the number of seconds in between these calls to clock, which is how long your algorithm took. That's how you can do it. All right. Any questions about that? So I have one more section for us today, and it is about sorting. All right. And again, this is more of a 41 honestly, it's more of like in an algorithms class at a 4-year college topic, but I want you to understand them a little bit now, because you've used like the sort function from the algorithm library. Let me tell you kind of how it's working, right? So I promise not to test you very much on this. Again, if I ask you any questions about sorting on the test, you can just come back to these slides and read off the answer most likely. All right? So to get in the mood for sorting, pretend I have a bunch of numbers. Here are my numbers. 18, 23, they're out of order, right? I like to sort them into sorted order. So like the 7's the smallest, it better eventually be at the start, right? But pretend I have a bunch of numbers, and I tape them to the whiteboard. There's like a bunch of papers, one for each of the numbers. How would you, as a human, I give you like a stack of cards in this order, and you have to like sort them. How would you sort this list? How would you do it? And then my hint for what I'm going to show you later, most of us as humans, we naturally choose a sorting algorithm called selection sort or a sorting algorithm called insertion sort. And I'll show you what those are in a couple slides. But take a couple minutes to discuss with your partners, how would you sort this list? Like, what would you look for? If you had a physical stack of papers, or if they were arranged on the whiteboard, how would you move them to make them sorted? How would you create a sorted list from an unsorted list? What is your algorithm? All right, the conversation sounds to be dying down. Does anybody want to share their sorting algorithm? Like, what would you do? I gave you a physical stack of papers, or arrange them right next to each other. How would you sort these? It's not a trick question. It's just like, how would you do it as a human? Yeah. So what does that mean? Like, tell me exactly what you would do. Like, what would you grab first and put where? Okay. But I think I'm giving you that in that order anyway. That's my idea. I'm giving that to you. How would you sort them, though? How would you make it smallest to biggest? Okay, so you'd look for the 7. You'd see the 7, grab it, put it at the front. That's your idea? Yeah, that makes sense. 7, then you'd put the 8 before that, etc., etc. Did anybody else come up with another idea for sorting? That's probably what I do too. Cool. Or if you have like a stack of cards, like if you ever play some game involving playing cards, there's actually a different algorithm where maybe like I'm looking at these two. I have just the first 3. Let's sort those, then put a new one in, then put another one in. It's hard to explain, but this might be a natural thing. And if this was the way that you chose to sort stuff, that is called selection sort. There's another way that I will explain better with a diagram called insertion sort. That might be something else that you've done before as well. But yeah, these are just normal ideas. We're just putting them in code. That's all. So I have a really fun website to go to, and I'm going to give it to you on Discord if you want to look at it too. It'll just take, 2 minutes for my Discord to start it. But here's the idea. This is a randomized array. I can randomize it some more. And the numbers in the array in order are at the bottom there. What it's trying to show you with the bars is like relatively how big that number is relative to everybody else in the array. So that's what the bars mean. And so once I show you these sorting algorithms, it's going to give us a nice, cool, animated description of them. Once the sorting algorithm is complete and this array is sorted, we should see a nice increasing line of bar heights. That's what's going to make it look pretty. Okay. And I'll give you this when Discord opens, which seems to be now. It's getting there. Trying. So here's the link if you want to go to it. Honestly, it might be faster to just type it or search in Google for it. But that's okay. So now you have it, and I'm closing Discord before my computer catches fire. All right. I do not want you to memorize any of these. Here's the code. You can look at it later if you'd like, but you can always look it up in a book or on Wikipedia. I just want to tell you the general idea behind all these sorting algorithms, right? So the first one's called bubble sort. And bubble sort is super simple and super naive, I guess, but it'll eventually get the job done. Bubble sort, all it does is it just zooms in on 2 consecutive elements in the array. It zooms in on them, and it looks and it sees how do they compare with each other. So here's my, here's my example array. Man, why do we have to do computer science at a time like this? So this is going to eventually become sorted, right? This is going to be transformed into 3, 5, 6, 7, 8. But let me show you how bubble sort chooses to do it. All right, so here's the unsorted array, 8, 6, 7, 5, 3. And it's going to do something really weird. It's going to look only at, it's only going to look at the 2, I wonder if I can do this. Yeah. It's going to look at the 2 elements that are right next to each other. It's going to zoom in on just those, and it's going to be like, all right, how do 8 and 6 compare? Are they out of order? Yes? All right, I'll swap them. So this becomes 6, this becomes 8. That's about 8. And then it just scoots over, and it's like, all right, I have 8 and 7. Are those out of order? If so, I will swap them. So it only looks at 2 things right next to each other. So this is now 7, this is now 8. The thunder is stealing my thunder. And then we're going to, oh gosh, let me just draw again then. And then it'll look at the next 2 consecutive elements, the 8 and the 5. Are those out of order? Yes. Five and 8. It'll swap them. And then it looks at the last 2 consecutive elements. Are those out of order? Yes, so it'll swap them. 3 and 8. And now we've gone through the array once, looking at every consecutive element. Everybody's out of order except for that 8. Right? So we have to do it all over again for everybody else. But after one iteration, we know that this one's going to be in the right spot. That's what bubble sort can guarantee. So I only ever have to like do that game all over again for this one smaller array now, which is nice, but still kind of horrible. So now I go and I look at these and I swap them if they're out of order, etc., etc. So every time I go through every piece of the array, I have the last element in the right spot. I go through it again. Now this element's in the right spot. I don't have to look at them again. I'll just sort the rest of this array. That's what bubble sort does. All right. It sorts an array by swapping elements that are right next to each other. And so here's the algorithm. It's going to be a doubly nested for loop. So the I variable is going to keep track of how many like swaps we have to do in the worst case. We're going to swap through we have to visit every consecutive index of this array that we're looking through. All right. And then J will keep track of like, all right, what's the last index that I care about? Because every time that I go through the array, like this one's now in the right spot, so I don't have to look at this one ever again. Well, that's fun. Yeah. Have I got a flashlight? Well, I'll pause the recording.